and people can contact us if they want to do experiments. So I'm not going to present about psychedelics today because that's a whole different rabbit hole, but feel free to contact me. Today we're going to focus on sustainable mushroom production because nobody talks about mushrooms anymore, right? So it seems like the world is getting smaller, doesn't it? And although the future of the world is rather uncertain, it's projected that global population can increase by up to 33% by 2050. This will increase food demand, resulting in 70% increase of crops needed to sustain these populations. And unfortunately, anywhere from 33 to 50% of global food produced never ends up being eaten, contribute to energy loss and waste accumulation. The World Bank estimates that there could be as much as 3.4 billion tons of annual global waste being produced by 2050. And the vast majority of this waste would likely be compostable products like food, paper, pulp products, and this type of things. And these could be used for mushroom food. So many mushrooms of nutritional and medicinal interest are considered saprotrophic, meaning they feed off dead and dying organic matter. This is important considering the large amounts of organic waste being produced globally. Mushrooms generally have relatively high nutritional protein content. They produce antioxidants. They also produce beta-glucans, which are like huge in research today. Also, the CO2 produced from mushroom respiration can be collected and used for different things, which we'll get into. And byproducts from mushrooms can also be used for bioenergy, compost, animal feed, which are all important considering that there's lots of inputs required with current methods of producing these. So today's global mushroom industry is largely suboptimal for a few reasons. Currently, China produces more than 70% of the world's mushrooms, which comes with high energy demand for shipping globally, excessive lead times for obtaining product, and potentially different quality control standards. The most commonly used commercial mushroom substrate is sawdust, which are packed into plastic bags to make artificial logs. And often these artificial logs aren't used to their full potential because continuous production is associated with diminishing yields, and mushroom farmers would rather just use new substrate. So the old substrate generally ends up in landfills, which results in hundreds of billions of tons of waste. And then sawdust is often collected from sawmills, which must be washed to remove toxic substances like juglone from walnut, and also fungicides that can hamper mushroom development. And although there's much research initiatives looking at different mushroom substrates, they're largely not being adopted. So let's take a deep dive into the current literature. So a 2020 study looked at the impact of integrating corn husks into sawdust substrates for growing oyster mushrooms. They looked at sawdust substrates that contain different quantities of corn husks, although they found that the substrates containing corn husks took longer for mycelial to fully colonize the substrates. Initiation of fruiting bodies actually occurred faster. There was no difference at the speed in which fruit developed. They found very little difference in the relative amount of time the whole process took. And there was no difference between the sizes of mushroom caps, but the stems lengths were reduced, which is indicative of good mushrooms because generally you want the big beefy caps and the small stems. They also reported higher yield of fruiting bodies, higher mushroom fresh weights, higher dry weight content, and negligible differences in moisture content, which means that not only were more mushrooms being produced, but the biomass per mushroom was increased since the dry weights were increased and the moisture content stayed the same. Here they show biological efficiency increases with increased corn husk substrate composition. So corn husk has the potential to be used as a sustainable amendment to current oyster mushroom substrates or replace them entirely. So with corn being an important staple crop for both human consumption and animal feed, using corn byproducts to produce mushrooms could help improve the sustainability of both corn and mushroom production. So Here's an interesting one. There's a recent paper that looks at different commercial alternative growth substrates with added diaper cores for growing reishi, which is an important medicinal fungus. So diapers, let's think about this, okay? More people, more babies. More babies, more diapers. More diapers, more food? It could be a thing. So they looked at commercial growth substrates made up of sawdust amended with rice bran and different things. They added different amounts of diaper to the substrates at 1, 2, 4, and 5%. They also made additional experimental substrates out of commonly occurring food waste, such as coffee grounds, banana skins, this type of thing, and added diaper to those. So all the treatments consisting of the standard media with diapered allowed full mycelial spread within 6 weeks. But those containing 4 and 5% diaper allowed full media colonization and fruit harvest in a significantly less amount of time than the standardized control. Of the treatments that included additional waste material, only that with the largest amount of diaper material and that which included a larger amount of commercial substrate allowed full mycelial colonization within 6 weeks. Additionally, the treatment with the commercial substrate was the only one that allowed full colonization to occur in significantly less amount of time. So ultimately, this shows that of the waste products tested, the diaper was the best. So when it came to yield, treatments containing 2% diaper produced fruit that was significantly larger in diameter and overall mass. And the 2% diaper treatment also had the highest biological efficiency. Now, the treatment with 2% diaper also resulted in the highest substrate block weight reduction, which was about 70%. And as I stated before, lots of the times the mushroom farmers don't use the full extent of their substrate, which gets put into the landfills, and a 70% reduction in weight could result in a 70% landfill waste reduction. So that's good. So sustainable production of both gourmet and medicinal mushrooms is possible by incorporating different organic byproducts in common substrates. These practices could allow high yielding production of quality mushrooms and with increased biological efficiency and provide additional income to farmers and maybe even daycares. There's a high potential to reduce the amount of landfill waste for both plant and mushroom agricultural practices. It could decrease food production costs, and it could also broaden the scope of mushroom production to make it more adoptable practice globally. Next, we're going to look at a 2021 paper which examines CO2 utilization for co-cultivation of mushroom and lettuce. So CO2 generated through mushroom respiration actually inhibits continuous development of the mushrooms. And current CO2 fertilization processes at greenhouse often rely on burning fuel. So if we could capture the CO2 from the mushrooms, we could allow sustainable production of mushrooms and different crops together. So this diagram presents the closed cultivation system used, consisting of a mushroom chamber, an air mixing chamber, and 3 lettuce growth chambers. The implementation of the mixing chamber maintained the CO2 concentration between 1,000 and 2,000 ppm, which would be ideal for this purpose. So essentially they proceeded with 2 different methods of using this system. One, which was non-continuous, where lettuce and mushroom specimens were put into the system at the same time. And the other one being a continuous system where lettuce and mushrooms were integrated at different times to stagger the time frame of integration. The non-continuous system, the photo periods were the same, and the continuous system, the photo periods differed to allow 2 of the 3 chambers to be actively photosynthesizing at the same time at all times. So the authors ran these 2 systems for 5 days each and repeated the runs for 3 times each. So they collected the data related to CO2 concentration and biomass accumulation of the lettuce and then ran a simulation to simulate 50 days. Data shows that the non-continuous method allowed CO2 concentration above 1,000 ppm for 400 hours, followed by a rapid depletion in CO2. And then between 600 and 800 hours before it was depleted. Oh, sorry, it went back up before it was depleted. And the continuous system actually allowed better maintenance of CO2 at 1000 ppm for 50 days for the lettuce and around 2000 ppm for the mushrooms, which was ultimately a better strategy. So using the continuous cultivation system, lettuce would develop significantly higher shoot fresh weights and dry weights by 25 days compared to those produced not in the system. And also, leaf area looks pretty good too. So using the continuous cultivation system, lettuce would develop, they found that the continuous system would result in around 80% reduction in CO2 emissions compared to mushrooms cultivated outside the system. So this doesn't even take into account the CO2 produced from conventional lettuce production. So ultimately combined would be a much greater effect. So the mixed continuous co-cultivation of plants and mushrooms make it possible to reduce CO2 emissions and improve plant productions to achieve more sustainable agricultural methods. So such intercropping systems can allow high yielding production methods for plants and mushrooms simultaneously, which could facilitate the reduction in CO2 emissions related to current mushroom and plant production protocols. It could enhance the efficiency of current methods. This paper also presents a method for modeling data to reduce input time and costs associated with developing and validating these methods. And intercropping these could ultimately allow more efficient use of space and condense the space required for to develop crops to feed the world. Next, we'll look at a 2022 paper that presents a method of bioenergy production using mushroom waste. That's kind of cool, eh? So ladies and gentlemen, the Mako composter serves all your composting needs. So what they did was they add 30 liters of raw dried mushroom waste and 9 liters of water, and they ran the system at hourly intervals. After composted products were acquired, they were pelleted and used for testing. The pellets were found to have low sulfur content, indicating high environmental compatibility, and low hydrogen per carbon ratio for high thermal efficiency. So the experimental samples were composted anywhere between 1 to 5 hours and then pelleted and compared to an uncomposted, unpelleted control. All experimental samples seem quite suitable for combustion with less than 10% moisture content. High volatile matter allows combustion at lower temperatures, which is important to reduce the inputs required when burning this. Fixed carbon acts as the main component of energy, and this remained at good levels. Ash is actually the main byproduct of these experimental samples and was considered appropriate levels by international standards. So caloric values indicate the overall combustion properties in relation to potential energy. The national standard of low-grade coal is about 16.3 megajoules per kilograms. Composting process increases this value to above the standard. As we can see, the control is below the standard. Mass density increased with composting hour, which were found to be within the acceptable ranges of 1,400 or 4,000 kilograms per meter cubed. And then energy density gives the amount of energy per area, which also increased with increasing composting time. The values obtained are very similar to commonly used coal pellets and roughly double those of raw biomass products. So the 4 and 5 hour treatments had the most appreciable mechanical properties and were thus deemed more suitable than the 1 to 3 hour treatments. The combustion process and thermal stability of the 5 hour treatment pellets were then tested. So between 1 to 200 degrees Celsius, about 4% of biomass was lost due to loss of water. In the next stage, about 50% of mass was lost due to burning of volatile compounds. And then the final amount of mass was lost, which was about 36.56%, which was exactly 30.6456%, representing oxidation of fixed carbon. So this tells us that this product is suitable for practical use and the thermal temperatures required to actually implement them. So composting and pelleting raw mushroom byproducts can reduce the amount of mushroom waste from different industries. The bioenergy pellets produced have good thermal efficiency, low ash content, high caloric value, making this an efficient option with abundantly available starting material, high environmental compatibility. The pellets have good mechanical properties, allowing high durability and transport and also storage. With a 4-hour treatment actually being the best combination of mechanical properties and energy efficiency. With the proper tools, these pellets can be made easily in a small amount of time and have broad potential for use. Ultimately, this represents a feasible alternative to burning coal. So although we don't know for certain if the global population will continue to increase at the extent forecasted, we need to make an effort to be prepared for what is to come, consider different ways to enhance food production while reducing waste byproducts and maximizing space. Sustainable mushroom practices show potential to create global circular economy to enhance food production practices that can be applied on a broad scale with minimal resource input. Implementation of these practices can result in reduction in fuel input and gaseous emissions and minimize spatial requirements. And by doing further research and development related to sustainable mushroom practices, it's possible to broaden the scope of applicability. Some mushrooms feed on radiation, can be applied to bioremediation. Some mushrooms are currently being used for textiles to create mushroom leather. So really the sky is the limit. Implementation of these refined practices can allow a reduction in the land necessary for landfills. And these emerging methods could also increase land use efficiency for agricultural practices. So ultimately, with potential future uncertainties related to sustainability, food production, and spatial availability, there's so much room for mushrooms. Thanks, guys. Questions? Can you talk about the vitamin G pellets? Was that like mushroom that you use higher in mushrooms, or like the stems, like the mycelium, and the base? Yeah. So sorry, if you want to repeat it.
Okay, yeah, I'll repeat the question.